Now we'll turn public key cryptography into working code. You'll generate a key pair, sign a message with the private key, and verify it with the public key. The same pattern used in crypto wallets and passwordless login. You've already built the foundation: how blockchains preserve data, how web apps trust users, and how keys prove identity. In this module, we'll connect those ideas by signing and verifying messages in JavaScript. A digital signature works like a tamper-resistant seal, but with math instead of ink. When you sign a message, you prove control of the private key without exposing it. Anyone with the matching public key can check whether the signature fits that message. That is why wallets can authorize transactions and apps can confirm ownership. The key point: signing does not hide the message. It proves origin and integrity, while the content may still be readable. Think of the signature as tamper-evident. Signing combines the message with the private key to create a signature that is bound to the exact contents. Verification then uses three things: the message, the signature, and the public key. It answers one question: does this signature match this message from this key? If yes, trust the integrity. If not, treat it as changed or invalid. For this demo, we'll use Node.js's built-in crypto module that keeps setup simple, with no extra packages to install, while still using real public key cryptography. We are not sharing a password. We generate a key pair, sign a message with the private key, and verify it with the public key. Wallets may use different APIs and curves like CCP 256K1, but the signing pattern is the same. Before writing the signing code, we need a tiny project we can run locally. Make sure Node.js is installed, then create a folder for the demo and move into it. Inside, create one file named signverify.js. That file will hold both the signing and verification logic. To test it, run node signverify.js from the terminal. A key pair is created together, not as two unrelated random values. In Node Crypto, generate key pair sync with ed25519 returns both public key and private key. The private key is your proof of ownership, so it stays secret and is used to sign messages. The public key is safe to share because it only verifies signatures. The math links them, but the private key cannot be practically derived from the public key. If you lose it, you lose that identity. A digital signature is not a general approval. It is bound to the exact message that was signed. Login to app and login to app produce different signed data, so the original signature should fail if that exclamation point appears later. This is why authentication often uses a fresh challenge or nonce. The user approves one precise request, and the system can detect tampering before trusting it. Here, we sign one fixed message. Sign in to example app. The signing function takes that message, converts it to bytes, and combines it with the private key to produce a signature. The private key is not sent anywhere. It is used locally during signing. The output can be stored or transmitted as hex data. Remember, signing does not encrypt the message. It proves this exact message was signed by the matching private key. Verification is the mirror image of signing, but it uses the public key. The verifier checks the original message, the signature, and the claimed public key, then returns true or false. True means the signature is valid for that exact message and key pair. Change the key, alter one byte of the message, or swap the signature, and the result becomes false. The full sign and verify cycle fits into one runnable example. First, the program generates an ed25519 key pair. Then it defines the exact message the user is approving. The private key signs that message, producing a signature. Finally, the public key verifies that the signature matches the same message and key pair. If the message, signature, or public key changes, verification fails. That is the core trust check behind wallet authentication. One of the best ways to trust your signature code is to try to make it fail. Change the message, swap in another public key, or damage the signature bytes. Each test should return false. If any of them still verifies, something is wrong. These failures prove the signature is tied to one exact message and one matching key. This demo maps directly to how wallets work. A wallet holds the private key and uses it to sign something specific, either a transaction that moves assets or a login challenge that proves control of an address. The private key never leaves the wallet. What leaves is the signature. Then the blockchain or app backend verifies that signature using public information and accepts the action only if the proof matches. The same pattern also applies to login. Instead of asking the user to remember a secret, the server creates a fresh challenge. The wallet or authenticator signs that challenge with a private key the user controls. The server checks the signature against the matching public identity. If it matches, the server knows this is the rightful holder and can safely create a session or issue an access token. You now have the core pattern behind wallet authentication. Prove control of a private key by signing a message, then verify it with the public key. If the message, signature, or key changes, verification fails. Next, we'll connect this idea to real wallet login flows.